So far, all the integrals you've seen have been of two different kinds. The first kind of integral you saw was indefinite versus definite. So an indefinite integral was just the integral of f of x dx. That was it. So what's it missing? What is an indefinite integral missing? Bounds. So that's the difference between indefinite and definite. Definite would have bounds a to b of f of x dx. And when you have the bounds, it means a defined area, right? We've learned that integrals mean the area from one point to another bounded above the x-axis. So that's when we have defined bounds. Then we get to what we're going to introduce today, which is improper. All right, improper integrals are where one or both of the bounds are infinity. Fun. Okay, so how's that possible? How's it possible to find the area when one of the bounds is infinity, or both of the bounds, or is it possible? Okay, well, you have to get to talk to, well, does the area converge or diverge? That's what we're going to get into. So we've got indefinite integrals, which we're comfortable with, definite integrals, and now improper. So either it's going from a to infinity, that's one kind, or it's going from negative infinity to b, that's another kind, or it's going from negative infinity to positive infinity. So those are the three different kinds of improper integrals. So how do we deal with them? We do a substitution, and we get rid of the integral bound that we don't want there. So let me show you how that works. So the question, our first question is, starting at 1 and going to infinity over the function 1 over x dx. Is it possible, does the area, starting at the number 1 and going all the way to infinity, does that area converge or on a single number, or does it diverge? So visually, we're thinking about the function 1 over x is a hyperbola that comes like this. If we start at the number 1, does the area bounded beneath the curve and above the x-axis as this goes out to infinity, does that area seem to converge? And it does. It seems to converge because it's compressing, the part of the hyperbola is compressing on the x-axis, and so we feel like the area should converge on a single number. So visually, our gut tells us that yes, this does appear to have convergent area. Here's how you're going to do it. You're going to go from 1 to b. Instead of 1 to infinity, and then you put the limit that b approaches infinity on the outside. So you're going to replace, you can't leave the infinity as a bound, but you can have infinity as part of your limit. So then you're going to evaluate that antiderivative, evaluate that integral, and we know that the antiderivative of 1 over x is what? ln what kind of x? Absolute values. Okay, natural log of the absolute value of x is the antiderivative plus c on bounds that go from 1 to b. And so the limit as b approaches infinity would be applied to the natural log of the absolute value of b minus the natural log of the absolute value of 1. Then we substitute in that b is approaching infinity. So we'll have the natural log of the absolute value of infinity minus the natural log of the absolute value of 1. The natural log of infinity is what? Still infinity. Minus the natural log of 1 is 0, so that is infinity, which does not converge, even though the area looked like it was. The value of this is infinity, and so this is divergent. What that means is it's not possible to determine an answer for the area under that curve, because no matter how far you go, you'll still get more area. Even though it's teeny tiny, the area way, way, way out there is still accumulating positive area. So this is a divergent area and a divergent improper integral. You always take the bound and replace it with a value. Okay, let's try another one. And sometimes the results are surprising. Okay. How about the integral that goes from negative infinity to positive infinity over the equation 1 over 1 plus x squared to the dx. All right, sometimes it helps to look at a graph of this. We're going to skip that part just for the sake of time. What we're going to do is we're going to use one of the properties of integrals that says you can separate an integral. So this would be equal to the bound from negative infinity but stopping at 0 of 1 over 1 plus x squared dx added to starting at 0 and picking up at up to infinity. So I've just basically split this integral up at the number 0. Is 0 important? No. I could have picked any number to split up this integral because the domain of this is all real numbers. So I could pick any real number and split up this integral into two pieces. I just happened to pick 0 because it's an easy one to plug in. Once you've separated the improper integral into two separate improper integrals, then you'll do the same thing we did last time, and you will apply a limit to each piece. So in the first one then, I'm going to replace the lower bound with a, and a is going to approach negative infinity. And for the second integral, I'm going to replace the upper bound with b, and b will approach positive infinity. Then we find the antiderivatives. All right, what is the antiderivative of 1 over 1 plus x squared? Yeah, all of these are going to be have perfect antiderivative, or most of them have perfect antiderivatives. Okay, so this one is tangent inverse. So this is the inverse tangent of x plus the constant c going from a to 0, where the limit of a is, oops, I didn't write it correctly, did I? Stop me, okay, I forgot my negative right there. Okay. All right, and then the other one has the same antiderivative, of course, so the limit as b approaches positive infinity of tan inverse of x plus c, and this one goes from 0 to b. And now we'll plug in. Okay, the inverse tangent of 0 minus the inverse tangent of negative infinity plus the inverse tangent of positive infinity minus the inverse tangent of 0. Okay, what is the inverse tangent of 0? 0 pi. Minus. Okay, so think about the way tangent is shaped as a graph. Right? So tangent's like this with two asymptotes on either side. Okay. All right, what is the inverse tangent of negative infinity? So it's asking, when does tangent hit negative infinity? Well, we know it heads to negative infinity right here. What's the value? Where is it hitting there? Negative pi. So it's minus negative pi over 2. Sorry, not pi over 2. Plus, okay, when does inverse tangent hit positive infinity? Positive pi over 2. And then minus 0 pi again. So that means I end up with pi over 2 plus pi over 2, which is pi. And so this area does converge, and it ends up to have a value of pi. This is convergent improper integral. Got the picture? Mm-hmm. Yep. All right, let's try another one. Let's do the integral from 0 to infinity of 2 over x squared plus 4x plus 3 dx. I only have 1, so I'll do b as my upper bound, so 0 to b. Okay, who remembers? Okay, we've done the integral of 1 over x, that was easy, natural log of x. We've done the integral of 1 over 1 plus x squared, that was an inverse trig. How about this one? The addition thing, right. Okay, partial fractions, right? So we would separate this into a over the factor of x plus 3 and b over the factor of x plus 1. And then you're going to work out your partial fractions by cross multiplying. I am not going to spend the time doing that right now, but I will tell you that a turns out to be negative 1 and b turns out to be positive 1. Now those have nice antiderivatives. And so the antiderivative of negative 1 over x plus 3 is what? Negative natural log of the absolute value of x plus 3 plus, and the antiderivative of 1 over x plus 1 is the natural log of the absolute value of x plus 1 plus c going from 0 to b. All right, what happens when you add or subtract two natural logs with each other? Okay, so these two are, well, one's a negative and one's adding. So that really means in the properties we could write these as the natural log of the quantity, and or the absolute value. And what would go on top? Which one? The x plus 1, and then the x plus 3 on the bottom, plus c from 0 to b. So now we can plug in. We're going to have the natural log of infinity plus 1. No. I got to divide through by the highest power of x. Okay, the limit as b approaches infinity. So if I'm going to do that, then I have to have the natural log of, and I have to divide x plus 1 and x plus 3 by the highest power of x. So 1 over 1 over x and 1 over 3 over x. Okay, now I can plug in. So I will have the limit the natural log of the absolute value of 1 plus 1 over infinity over 1 plus 3 over infinity minus the natural log of the absolute value of 1 plus 1 over 0 times 1 plus 3 over 0. All right, this one turns out to be the natural log of 1. This one turns out to be the natural log of 1/3.
1 over 0 and 3.
It's 1/3. Let me show you. The dividing by, I should have, that technically the right way to do this would have been, let me insert a step here. Nope, insert a step up here. I should have separated this. Limit as b approaches infinity. We should have had the natural log of the x plus 1 over the x. No. Yeah, it only applies to this one because the limit's approaching. And then minus the only one I need to divide by, and this is where you're plugging in. I'm skipping things and not doing a good job because I'm trying to go too fast for you. This is where the b is, and this one is where the 0 is. Hold on, erase. There we go. Yeah, so the only one you have to divide through by the highest power is the b part. You don't have to divide through by the highest power. Another way to think of it is, how would you get rid of the 0 denominators? Like, put it back. Okay, so what do? Multiply everything by 0. Feels weird, but multiply this by 0, multiply this by 0, multiply this by 0, multiply that by 0. So these zeros reduce, these zeros reduce. You end up with 0 plus 1 over 0 plus 3, which is 1/3. Okay, but what's the natural log of 1? Okay, and the natural log of 1/3 is really the natural log of 1 plus the natural log of 3. Or the negative, if you want to do it this way, I'm distributing my negative. Natural log of 1 minus the natural log of 3, distribute the negative here. So we end up with 3, and it converges. Natural log of 3. Okay, last one. One to infinity of x e to the negative x dx. All right, so we did 1 over x, which is natural log of x. We did 1 over 1 plus x squared, which was inverse tangent. We did the one that just required partial fractions. What's this one going to need? Oh, integration by parts, your favorite. So we even talked about the test yesterday for that. What is it? The acronym, the funny acronym? LIPIT. All right, so we need the LIPIT test for this. So according to the LIPIT test, which one would we choose as our x, or our u? Okay. Yeah, p is polynomial, right? So we're going to use our u is going to be x, which means our du is dx, which means our dv was e to the negative x dx, which means our v is negative e to the negative x. So we have our integration by parts that we're ready to do. So this is going to be the limit as b approaches infinity of, okay, u dv, so that would be x e to the negative x minus the integral from 1 to b of, okay, v du. Did I add? I added a negative, yeah. Okay, minus v du, so which will end up to be a plus e to the negative x dx. And that has an easy antiderivative. So negative x e to the negative x minus e to the negative x plus c going from 1 to b. And then we plug our b in, and we plug our 1 in. So negative b, e to the negative b, minus e to the negative b, plus 1 e plus 1e. To the negative 1. Oh, I forgot my limit out in front. Okay, then we plug our limit in, so limit of all of that. Okay, and that goes to 0, and that goes to 0, and that goes to, and so we get 1 over e plus 1 over e, which is 2 over e.
Even if infinity is not in front, if it's to the negative infinity, 0.
Yeah, because of the growth rate,
Right.
so that we know the, yep. I'll see you guys in our chapel row.